Okay, welcome back, you guys. In this video, we're going to talk about power and what it really means and how we might look at it and apply the idea of power and how we use it in real life. So, first, the definition of what power is. Basically, it's how quickly work gets done. That's it. How quickly work is done. So now the thing is, what we know about work from the work energy theorem, what work does is if there is some total value of work that is not canceled out, then we see that work changing the energy, specifically the kinetic energy of an object. So since the work changes the kinetic energy, what we know about power is that it can be thought of as the rate of change very important phrase, the rate of change of energy. And that means something for us mathematically as well. So we have this idea of power, capital P for power. And it's how quickly work is done, the rate of change of energy. Well, we could do change of energy as a delta K, but we know that work equals delta K. So, and then the rate of the work getting done. So we divide by time. Work divided by time. You could do equivalently change in kinetic energy divided by time. Same idea. Now our units here for power are the joules per second. So we have joules for joules for work, or joules for change in kinetic energy, and divide by seconds for a time. Well, 1 joule per second is equivalent to 1 watt. And the symbol would be a capital W. Okay, so here's where things kind of get pretty lousy for us. We have a capital W representing work, and we have a capital W representing watts. And how do you tell the difference? Well, context. If you have a number in front of the capital W, then the W is likely trying to represent a unit of power. If there is no number in front of the capital W, then it is likely trying to represent work. And you just have to pay attention to the difference and to the context where the capital W is being used. So one more thing about this before we move into some other interesting ideas is this is going to represent the average power. It won't often be called average, but that's really what it is. And we'll go with that convention, average power, unless otherwise stated. Just a little kind of a side note. Now, watts. Okay, it's named after James Watt, way back in the I don't want to say the late 1700s. James Watt was kind of instrumental in getting the Industrial Revolution going, worked a lot with steam engines and improving their design. But there's another unit of measure that's very common for power, and the other unit that you are probably used to hearing is horsepower. Particularly with cars, but not always. But the horsepower is equivalent to 746 watts. Both a measure of power, but this is just a little, I'll put a 1 here for equivalency, just a little conversion, because you'll hear horsepower, you'll be asked about horsepower, and you want to be able to at least make the conversion mathematically, if even if it's not all that intuitive. All right. So what's the deal with power? Well, first, we can look at motors. So as this idea of power applies to motors, and this could be electric or otherwise, doesn't matter, any kind of motor. They're typically all rated in terms of power. I'll call it power output. Now, most motors can do a variety of tasks. And what that means is you take a given motor, might be this big, or you take a motor might be this big, and each motor might be able to do a similar amount of work. You know, the little one can do that amount of work, the large one can do this amount of work. The difference will be how long it takes each one. So how quickly they get that work done is the time. And so you look at the work done divided by the power output of the motor, and if the power output is larger, typically from a larger motor, then it will take less time. And a smaller power output will, you know, decrease this value. It's going to take more time to get that same amount of work done. So real simply, a more powerful motor gets the work done faster. Awesome. Well, let's we're going to come back to this idea of motors and their power. But next, what I want to do is look at just an example, and it's actually a quite interesting one. So, back in 2003, well, back up a second, every year for decades now, there's been this interesting race, this competition. And the competition happens to be inside the Empire State Building in New York City. And it's a race. And it turns out it's in the Empire State Building. Of course, there are elevators, but there are stairs. Whole lot of stairs. And so on and so on. Okay, you get the idea. Well, the race is up the stairs, if you believe it or not. Holy moly. And in the Empire State Building, there happens to be a total of 1,576 steps in the Empire State Building. Wow. So the race is broken down by age group, and it just turns out that in 2003 there was a man by the name of Paul, and I believe you pronounced it Craik. He is from Australia. So back in 2003, Paul Craik won, and in fact he set the world record, and it still stands to this day, of 9 minutes and 33 seconds to the top of the entire Empire State Building's stairs. Well, here's what I want to do. If we understand how big each step is, so each step, you're covering a vertical distance of 0.20 meters, and let's say we have a mass for this gentleman, nice even number of, let's give it 70 kilograms. Okay. Well, then what was Paul's power output? There's our question. So, first of all, the man is insane, but incredibly fit. And for roughly 9.5 minutes, he was producing enough power to get his whole body, his entire mass, up at a certain rate. Remember, it's not just the fact that he got to the top, it's how quickly he got to the top that really matters here. So we're going to look at the power output. We need to know work done, and we're going to divide that by the time. Well, the work done is equal to a force times a distance. And we're going to divide that by the time. Well, the force that he is applying is simply a force to overcome gravity. So that force is equivalent to mg. And the distance traveled, that's going to be the height of each step multiplied by how many steps there are. And we'll divide by time. So I'm going to move this down. I'm not going to move over because I'm going to have a whole bunch to write down. I'm going to look at the mass. We have 70 kilograms. I'm going to look at G is 9.81 meters per second squared. Okay, so my distance, remember, the total distance traveled is the height of each step multiplied by how many steps there are. So I need both of those numbers next. There are 1,576 steps, and each step is 0.20 meters tall. So there's the numerator of this fraction. And so mass times gravity, mg, that's the force, and these two here represent our distance. Awesome. Well, the time. All right. 9 minutes and 33 seconds. I'm going to break this down. I need the time to be in seconds when I do a calculation for power. So 9 minutes. Well, there are 60 seconds in each minute, so I'm going to do 9 times 60. But then I have to add back on the 33 seconds, right? So I got a bit of number crunching to take care of, and then what I find is that Mr. Craik was producing an average power output of 378 watts. Well, what was that in horsepower? So I take my 378 watts, and I have an equivalency. I know that 1 horsepower is 746 watts. So this equivalency can be turned into a ratio that equals 1, and I can simply use that to cancel out watts and leave me with horsepower. Watts on the bottom, 1 horsepower, 746. There's that ratio. And when I do this work, for 9.5 minutes, Mr. Craik was producing a horsepower 0.51 horsepower, which is pretty remarkable. Actual horses really don't produce a full horsepower continuously. More closely to about 2/3 of a horsepower. So this is pretty remarkable. This guy was incredibly fit, even just to complete this task, let alone to do it in such a short time. Okay, so there's our example of power. Next thing to look at is this other interesting little tidbit. And it gets to something that that all of us are going to have to face at one point or another. So a little interesting note here. The power company, the electric company. So and the power company, that could be Southern California Edison, that could be Pacific Gas and Electric, PG&E, etc., depending on where you live. Well, they all measure energy use. They sell you energy. They don't sell you power. They sell you energy. But they measure the energy use, not the power, but the energy. In units called a kilowatt hour. What the heck? All right, well, the reason for this big mystery, conspiracy theories abound, don't know. Okay, but what we can do is pretty easily look at, well, how many joules are equivalent to 1 kilowatt hour. And this is not really hard to figure out. So we start with 1 kilowatt hour. And we know that that is equal to, well, the kilo is just 1,000 watt hours. All right. I can rewrite a watt as a joule per second, and I still have the hours multiplied by hours. Well, I know that in 1 hour there are 3,600 seconds. So I would have 1,000 joules per second times this hour, which is going to be 3,600 seconds. So what I'm getting to is pretty quick. 1 kilowatt hour is going to be equal to 3,600,000 joules. Here, seconds cancel when you do that multiplication. Or, alternatively, megajoules. So a kilowatt hour, yeah, it's kind of a lot of energy, but you can look at your electric meter on the side of your house. Apartments have them as well. Any place of residence is going to have one of these electric meters, and somewhere on there, depending on whether it's an old analog style or a modern digital style, somewhere it will tell you the current rate of energy consumption. Remember, rate of energy change or rate of energy use, that is power. That's true. But the electric company isn't, well, I should say they're not super concerned with how quickly you use the energy. It does matter because they need to be able to meet that rate of demand, but they don't sell it to you that way. If you use it a little faster here and a little slower there, they don't care. They just look at the total amount of energy measured in joules or kilowatt hours, total amount of energy that you're using. That's what you're billed for by the electric company, not how quickly you're using that energy. Although they're starting to look at some strange, wacky ways of changing their billing structure. Never mind that. When you guys get your own places, you're going to have a lot of fun with paying bills. So that was a neat little interesting thing. I want to come back to this idea of motors now. We're going to look at what's going on with motors once again. Okay, so we could see. I'm gonna do a free body diagram of. Let's use a car as an example. And our car has weight. All right, and because of the weight, there's also a corresponding normal force. It's like a reaction force. Cool. The motor will be applying a forward force to drive it forward. I'll draw that in just a moment. Whenever you're driving, even at a constant speed, so let's say this. Let's say we know at a constant speed, sum of forces will be 0, and that's going to lead to an acceleration of 0, and that's where we get our constant speed. Okay, brilliant. Well, sum of forces, the y is also 0, but that's sort of a given. The car is not flying away and it's not digging itself into the ground. When the car is moving along, though, the car will be experiencing some friction, kinetic friction, and opposing its motion, and will also be encountering some drag, air resistance. And in order to maintain constant speed, to maintain the sum of forces equaling 0, we need the motor to be producing a force to cancel that friction and just a little more to cancel the drag. So here's the force of the motor. Awesome. And so the motor is satisfying these conditions to produce your constant speed. But the motor itself and the force that it's applying really is also doing work. And as time goes on, it's doing a certain amount of work in a certain amount of time. So we can look at this and we can say to ourselves, even a car being driven at a constant speed requires power. The motor must apply this force in order to make our constant speed happen, even though nothing unusual is taking place. Now this force is in the direction of travel. Let's say our velocity is in the positive x direction as well. Okay, cool. So it's real simple that the work done by the motor is going to be the force of the motor multiplied by the distance traveled. Well, how is this going to look in an equation for power? We have the power produced by the motor. That's equal to the work divided by the time it takes. And the work is just force times distance. Force of the motor times distance. And then we're dividing by the time it takes to do this work. Awesome. Well, look at what we have here. We have a distance divided by a time. And that usually represents velocity for us. So this equation for power can be rewritten as the force of the motor multiplied by our constant velocity. So interesting thing to look at. If you want to go faster, it requires more power. But why? I mean, there's a couple things going on. It's not quite as simple as you think. Well, I'll just step on the gas, I'll make myself go faster, and I will need to produce more power to do that. Or I will be automatically producing more power to do that. Not so fast. So what is this going to mean for us? All right. So I'm going to compare two situations, same car. All right. And we're going to see how things change from one speed to another. We're going to say, well, you know what? The car has some weight. And that's kind of a constant thing. The weight of the car doesn't change depending on how fast it goes. There's going to be this normal force. And that doesn't change. That's a constant. So vertically, things are still canceling and just fine. One kind of an important, interesting thing about friction. So we have this force of friction. It was kinetic friction, right? There's our force of kinetic friction. Kinetic friction does not depend on speed. It doesn't change with speed. So here we're going to have a speed v1, and here we're going to have a speed v2, and we're going to say that v2 is faster or greater than v1. So slower situation up here and faster situation down here. Kinetic friction does not depend on speed, so it's the same in both situations. Excuse me. But something does change with speed. The faster you go, the more drag you create. So at slower speeds, you have a smaller drag force. At higher speeds, you have a larger drag force. And this is interesting because in order to maintain this constant velocity, remember we had to have this forward force applied by the motor just large enough to overcome those two forces. So here's our force of the motor. But in this situation, the force is sort of doing negative work on the car if we're traveling to the right in both cases, and these would be producing negative work. Well, we need to have the motor cancel both of those. We need a larger force out of our motor. And so what we see is that our drag force varies with velocity, and because of that, the force produced by the motor has to change. It is forced to, in order to maintain these constant velocities. So we'll look at this. Driving faster requires more power for two reasons. First, well, what's happening? Okay. Faster velocity, higher V, directly means larger power output. And we can see that from this simple equation, where if we increase velocity, we must be increasing the power. The second reason why driving faster requires more power is not quite as obvious, but we see it laid out right here for us. Drag increases with increased velocity. So the motor must create a larger force. To overcome that drag. At higher speeds. So in the first case, the first reason, larger velocity required a larger power output. In the second reason, here we see that the force required is larger at those higher speeds, which means even more power is required. So since both force and velocity increase at higher speeds. Sounds weird to say it that way, velocity increases at higher speeds. Well, yeah, but we're trying to think mathematically here with this relationship. Then the power needed to drive fast increases very rapidly. And what happens is you pretty quickly run into the limit of the motor. You pretty quickly run into the maximum power output. And no matter how much more gasoline you feed into the engine, you simply cannot create much more force out of it. And it just kind of reaches its peak power, and therefore you reach a maximum velocity. And there's other stuff going on as well, but that's it in a nutshell. Okay, so we've seen power. And I appreciate you watching. I appreciate you taking good quality notes. And definitely, if you have concerns about this, send me an email. And I'll be checking that the next day or two. I do expect you to take a day or two off, but also during this break, make sure you're staying focused. All right. Thank you for watching. I'll see you next time.